15 degrees.
I got 7.
Any others?
You put what was that? So the one of them was what?
Yeah, what we were just talking about.
So bad.
Oh my god. I didn't even know how to make Oh my god.
Okay, guys, let's look at these real quick. Probably many structures that could have been drawn. I drew 2. 30 valence electrons, did I get that right? Yeah. 1 DUS, I know I'm looking for 1 pi bond, which I put in that structure over here. I put one with a ring. Probably came up with others. Okay. Either line bond or covalent bond or long pairs. Questions? Let's see, functional group. The sulfide or thioether, either would work. There, what do we got? Ester? How we do? Longest bond would be 3. I'm sorry, not longest. Strongest bond. Strongest bond is 3. Because it's made using an sp orbital and an sp2 orbital. The others are made using like sp3, sp3.
Yeah.
You got to look at what orbitals are making your bond. Orbitals with more s character are going to make stronger bonds. Those are low in energy. Degrees of saturation, 12. Did I get that right?
Yes.
Did I get something else? Electrons in p orbitals, 22. Did I get that right? How we do on that one?
Can you show that?
Can you go back to the screen? Could you go back to the structure? I don't want to again.
22. How we do? 22? Who got 22? Good.
I put 11 pairs instead of 22.
What'd you get? How many? 4? I mean, each pi bond is 2 electrons in p orbitals overlapping. That's how you make a pi bond, right? I mean, you got how many pi bonds? 1, 2, 3, 4, 5, 6, 7, 8, 9 pi bonds. That's 18 electrons right there. But then sulfur, one of the lone pairs is in a p orbital. So anytime a lone pair is next to a p orbital, it wants to be in a p orbital. And the oxygen, where I put that lone pair on the right, is one of those electrons in a p orbital. We're told it's 22. Yay?
Yeah.
Question? The nitrogen electrons are in a hybrid orbital. If you graph the nitrogen, what's the hybridization of the nitrogen?
SP2.
sp2. There's only one up there, nitrogen. Okay, sp2. That means there's 3 hybrids and a p. What type of bonds do you see that nitrogen making?
Sigma bond to a carbon.
I see it making 2 sigma bonds. 1 to carbon and 1 to carbon. What else is it making? Pi bond to carbon. And all together now, what's that? Double bond to 1 carbon, single bond, sigma bond to the other carbon. Where's the lone pair?
And then it's hybrid.
Right here. Hybrid. That's why we, hopefully, graphing. There it is. Did you consider graphing it?
Oh, I didn't graph it, but I just...
I recommend graphing it. I think it's very powerful. That's the way I presented it systematically. Do it. Boom. There it is. Okay. What we got down here? 10 lone pairs and 19 hybrids.
On the sulfur, how it because sulfur can expand its oxidation. It was good. Some of them don't.
It's a neutral acid.
So it's always just.
It's only one answer. You put two long pairs there, it's no longer neutral.
You got more than two. You got one answer.
Okay, guys, this will be posted on 3rd floor in the glass case as you start walking down the hall towards the labs. 3rd floor. Let's get back to our IMFs, polarity. IMFs, also known as non-covalent interactions. We ended on hydrogen bonding. Okay, a hydrogen bond is just a very strong dipole-dipole interaction between two atoms. One of the atoms is the hydrogen, but it's only when the hydrogen is bonded to what? O, N, or F. Because when the hydrogen is bonded to one of these are very electron greedy, very pulling, leaving this H very electron positive. Lots of positives on the H. And that's called the hydrogen bond donor, the thing that supplies the H. Now, this will hydrogen bond to an O, N, or F. Really the lone pair. What's the charge of electrons? Negative. Okay? And so you got this negative here, these electrons. Lots of partial plus on the H because of the dipole pulling of these electronegative atoms, and you get this IMF between the lone pair and the H, sort of like Velcro. All right, real sticky. That's a stronger IMF than just some type of dipole like we showed in number 2. When it involves these types of H's or particularly strong, it gets its own name called hydrogen bonding. Just like with Velcro, don't you have to have 2 different pieces to make the Velcro stuff work? If you have 2 of the same pieces, they won't stick together. You got to have H bond donor and acceptor. All right. Then we can show a hydrogen bonding network here. That alcohol has a higher boiling point because of hydrogen bonding. The molecules have greater intermolecular attraction due to this hydrogen bonding IMF. This illustrates a hydrogen bonding sort of network. You can have maybe the lone pair of one oxygen hydrogen bonding to the H of another molecule. Or the H of that molecule can be hydrogen bonding to the O of another molecule. In this scenario, that would be the H bond donor, that's the acceptor. And so these molecules start sticking together pretty strongly. Okay. We'll see hydrogen bonds plenty. Hydrogen bond is often answered. Lots of questions. What holds your DNA together in a double helix? Hydrogen bond. Let's see what type of questions are here. Hopefully when you see questions in here, you've thought about these already. Okay. Now if you just got this guy, can that hydrogen bond to itself? No. I don't see a hydrogen bond acceptor or donor in that molecule. Now it can associate by dipole-dipole interaction because this is partial plus due to this dipole, and that's partial minus because it's pooling. And this partial minus could associate with the partial plus of another molecule. But that's not the strong hydrogen bonding. So no, it cannot hydrogen bond to itself. Now why do I say to itself? Because later on we may ask, can this molecule hydrogen bond to something else? Question, can this ether hydrogen bond to itself? No. It's just diethyl ether. Can it hydrogen bond? I see a hydrogen bond acceptor, the oxygen lone pair, but I don't see a hydrogen bond donor. Do you see an H that's on an O, N, or F in this molecule? No. You got to have both pieces for the Velcro to work. It can't hydrogen bond to itself, but can it H bond to water? Yeah, you see, you put it in water, and water, now you can get association between the lone pair and the H, this being your H bond donor, and this is your acceptor. Okay? So if someone says, can diethyl ethyl hydrogen bond, you need to say, are you talking about to itself, or maybe to something else? Make sense? How many H bond acceptors in this molecule over here? Effexor, antidepressant. How many H bond acceptors?
2.
Do you need me to clarify the question in any way?
No. Can a hydroxyl group serve as both an acceptor and a donor? And if so, do we count it twice?
Yes, it can, because a hydroxyl group has the lone pair, which is an acceptor, but it also has an H that's on an oxygen. So yes, it can act as both.
You count it twice.
But first, just acceptors. How many acceptors here?
3. Would you count each lone pair as a separate?
What's that?
Would you count each of the lone pairs on the?
There you go. That's what I was looking for. There's 2 lone pairs here. Do you count this as 1 acceptor or 2? I don't know. We need to clarify because I don't know the answer to that. I might say instead, how many H bond acceptor atoms? What if I say how many H bond acceptor atoms in this molecule? 3. That can probably H bond accept twice. But again, you may have to clarify questions. So, I'm not quite sure what to go with this here. Acceptor atoms. If we say acceptor atoms, the answer is 3. Oxygen, oxygen, nitrogen. How many donors? Let's see if this is easier. 1. Yeah, only 1. Right there. Now there's H's here. Are those H bond? No, that's not on an O, N, or F. Now since the H that's on an O or N or F is always drawn in, typically your H bond donors are going to be drawn in. So there's 1 right there. Can this molecule hydrogen bond to itself? Can you envision that? Let's talk about this. What about intermolecular? That is 2 different molecules. Maybe we could show another molecule. I'm not going to draw the whole thing, but okay. This is another molecule, and this is that CH2 nitrogen dimethyl coming off of another molecule. I'm not going to draw the rest. But if we have another molecule, let's put the lone pair here. This lone pair can associate with that H, and we can show some hydrogen bonding between 2 different molecules. Or I could have showed the oxygen associating with it, a variety. But that would have to be the donor. So that would be intermolecular. This compound can also do a question.
Yeah, can the OH group, can the hydrogen bond with the nitrogen or next to it within the same molecule?
That's exactly where I was about to go. What about intramolecular? Internal, within the same molecule. Very good point. Let's draw that bond out there instead of just having it. Okay, let's actually show the bond. Right there, we can get a sort of a intramolecular hydrogen bond. What size ring did we make? Now here. 1, 2, 3, 4, 5, 6. Is that right? 1, 2, 3, 4, 5, 6. Okay? It's like we're all holding hands here. Five here. But then you decide the hydrogen bond, nitrogen and H. Now we've got the 6-membered ring due to the hydrogen bonding. Now it's not a full covalent ring, but it is held together by some hydrogen bonding. That's not a covalent bond. It's a strong attraction. It's a non-covalent interaction. But these can hold things together like DNA in a double helix. Okay? So, go back up here. You have to envision these molecules being held together by that Velcro, where these are held together by the weaker, just simpler dipole-dipole, not as strong. Held together more, higher boiling point. Do we answer everything there? Looks like it. Let's move down to examples. These are two constitutional isomers. They have the same formula, different connectivity. Ethanol, boiling point is 78. Dimethyl ether, negative 25. That means even in your refrigerator or freezer, it's a gas. Why is this such a higher boiling point? Hydrogen bonding. See, can you envision a hydrogen bonding network between different molecules? Okay, can this hydrogen bond to another molecule of itself? No. You got two molecules sitting there and they both have acceptors. It's like, well, where's the donor? So they don't associate with each other as much. It's easier to get it to boil. You don't have to overcome as much IMF. Look at these constitutional isomers. Primary amine, that's a tertiary amine. Much higher boiling point. Can you envision hydrogen bonding between multiple molecules here? Like the network I showed up there? Molecules here, they only have acceptors. Question?
For before, when you did the intramolecular bonding of N and OH, if that makes a bond between the N and the OH intramolecularly, does that create another degree of unsaturation? Because it made a ring?
No, it would not. Not accounted for. It's not really a covalent bond. And the formula hasn't changed when you make the ring, so I mean, it's the same formula. Let's look at the next trend. Okay, water is 100. If you replace the oxygen with sulfur, it's actually negative 60. Okay? It means water's boiling point is 160 degrees higher. Why is it so much higher? Hydrogen bonding. Okay? Can you envision the network set up between the O lone pair hydrogen bonding to the H of another molecule because that H is bound to an O? Can this hydrogen bond to itself? I see neither an acceptor or a donor because a sulfur lone pair is not an acceptor and an H is on an S is not a donor. All right? And you really see the huge difference. Less IMFs here. Let's go to carbon. Question?
That would be polar.
It is polar. It does have dipole-dipole. But H bonding is so super strong dipole-dipole. Gets its own name. How about this guy? Sort of analogous. We have a carbon. We now have 4 H's because carbon makes 4 bonds. Look at it. I mean, this one is 100 degrees higher than this one. Why?
Bipolar.
Because at least this one has dipole-dipole interaction. That has no polarity at all. What does this have? The only thing it has is what? The only thing it has is van der Waals, but methane is pretty small, so it ain't got much van der Waals. Can you explain that trend with your IMFs? How about below? Let's look at butane, just plain hydrocarbon, versus, that's supposed to be an OH on the end, got a hole punched out there. Let's slip an oxygen in at each end. No, actually we're doing more than that. We're replacing carbons on the end with O's. Very similar molecular weight though. 200 degrees higher. Why? Hydrogen bonding. Okay, can you envision a network setup where all these, not only does each molecule have one sticky region, it's got two sticky regions. So it's like Velcro, double Velcro. Really holding those molecules together. All that's got is just weak van der Waals. Okay. That's all that had. Why is this 162 degrees higher than that? And more surface area. Butane. Butane lighter. Why is butane a liquid in the lighter? Because it's under pressure. Okay. There's your DNA. Like a CG pair. C's pair with G's. Why? Look how this is set up here. If you put these two different molecules close together, you've got the oxygen lone pair right there, able to make an H bond. You've got the H is bonded to a nitrogen right there, making an H bond there. It's like, you know, three right there. These two molecules just, boom, come together very nicely by hydrogen bonding. Your GCs go together in your DNA, and the other is what? ATs? Your ATs only have two hydrogen bonding. There's not a third thing down here that can hydrogen bond to maybe that lone pair. But in each one, what do you got? A purine and a pyrimidine. You've heard these terms in your biology. And then you get to the there's a magical double helix. All this is held together by what? Perhaps some other things too, but mainly hydrogen bonding. Okay, the fourth IMF is going to be ionic. Ionic is going to be your strongest. This is where you have attraction between formal ions, not partial plus, like in dipole-dipole. Even hydrogen bonding, you're dealing with partial plus. When we get to ionic, we're dealing with true formal positive and negative charges. These are going to have the strongest attraction and have the greatest influence. Sodium chloride. Boiling point 1413. You ever seen table salt boil? That's pretty hot. I didn't realize that was ever done. Now I'm only showing that's supposed to be it's a dash, it's an attraction. But really, what I should have illustrated is two different sodium chlorides interacting. All right. We can look at this example. Ethanol, boiling point is 78. If you make it ionic, remove the H and look like a sodium salt, boiling point is greater than 500. Basically, those ions now are going to lead to great intermolecular association, very large. And usually all your salts are solids, because they have so much association, they become solid. So that's your highest there. There'll probably be other things to say about these as we go along. Okay? I don't really want to just say things right now. We need to be speaking in context, and we'll refer back to these things. So that was boiling point. And when you talk about ionics, usually you don't talk about boiling. I mean, 1400 degrees, that's almost ridiculous to think about that boiling. too high. Okay, melting point. Melting point is going to be a very similar argument. Very similar ideas. The more IMFs, the higher the melting point. In general. There is a couple of exceptions to that general trend. You've got to weaken the IMFs to go from solid to liquid. Example. Look at these two carboxamides. Primary carboxamide, tertiary carboxamide. One has a melting point of 126, one is 44. Okay, we're on the Price is Right. Label them, see if we win. This one's 126, one's 44. Should be pretty easy. Now neither one is ionic, so let's not worry about that. What do you want to consider next? Well, the surface area is pretty weak. I would consider the stronger ones first. Okay, I think this has a melting point of 126. This has a melting point of 44. How we do? Me is a methyl group. CH3. I covered that in the nomenclature video. I know some of you have watched the nomenclature video. We typically cover that next week, but I'm asking you to watch that on your own. Okay? Why is this one so much higher? Yeah, can you imagine the hydrogen bonding network here? You could show it with the H, which is bound to an N, could be your donor, and then what could be the acceptor? The oxygen. That's kind of a trick question. Is that nitrogen a good acceptor?
No.
Why no? Very good. A lone pairs in the p orbital is not really basic or a good hydrogen bond acceptor. Okay? We'll see more of that. But this can hydrogen bond to itself. This can't, so less IMFs, lower melting point. Okay. Oh, there was another question there. No, that's it. Basically, when you get to melting point, it's the same idea as we did with boiling point. Let's look at solubility. And you're in the process of doing solubility in lab this week. Solubility is governed largely by your IMFs, and we covered the 4 main IMFs. Okay? And there's this adage, like dissolves like. A compound will dissolve best in a solvent with similar IMFs, or IMF possibilities. There's that question I was looking for, right here. Let's see if we can illustrate this. Which amide above is most soluble in water? Well, when I see water, I think of hydrogen bonding. Okay, water can hydrogen bond. You've got acceptor and a donor. Think of your strongest IMFs first. It's not ionic, so don't think about number 4. Go to number 3, hydrogen bonding. The stronger ones are going to like rule the roost. They're going to govern everything. It likes the hydrogen bond. Which one can it hydrogen bond to?
And both.
You can hydrogen bond to both. But it can form more hydrogen bonding to the first one. Okay? So for water, it's more H bonding. More H bonding to that one. What I mean by more, you could show a hydrogen bonding network with the H of water hydrogen bond to the oxygen. So you could do that for both. You could show the H of water hydrogen bonding to either oxygen, either molecule. But what else can you show for this one? You could show one of these H's hydrogen bonding to the oxygen. Can I just show both of them hydrogen bonding to oxygen? Where you can't do that over here. More hydrogen bonding potential is going to lead to greater association with water. It's going to love water more. All right? And thus it's going to be more prone to dissolving in it. What does it take to dissolve? The solvent has to basically really be intimate with the molecule and really associate with it, hug it, really like it. What's it going to be more soluble in hexane? Well, what do we know about hexane? Do nomenclature. Hexane is just a 6-carbon hydrocarbon. What type of properties does hexane have? What type of IMFs? All it has is van der Waals. I mean, it doesn't have any dipole potential or tighter bonding potential. All it has is van der Waals, so it's going to prefer compounds that only have van der Waals. That's kind of what light, okay? Now, kind of the opposite is, all it's got is van der Waals. It's not going to like a compound that's highly polar and got like lots of hydrogen bonding potential and lots of polarity. That's a different type of IMF. When we say light dissolves light, okay, question.
So I know the one on the left is going to be much more be able to dissolve water much better, but the oxygen on the one on the right also has lone pairs that would be hydrogen bonding acceptors. So would that dissolve in water as well?
Okay, you asked a good question because the question I asked was a relative question.
Right.
I said most soluble. I don't know if the compound on the left is soluble in water or not.
Okay.
I'm just comparing it to the other. Maybe they both are, or maybe they're both not. You understand how the question is posed? Okay. You're asking an absolute question. That's sometimes difficult. Usually, a lot of times what I will do is we'll judge relative to each other. The absolute, you'd have to go to the lab and do it. Or look it up in some table or something. You know, I mean, it can't hydrogen bond, but we got this ring over here, which is pretty much plain carbon, which is basically like just van der Waals. We can also introduce some terms now. They're probably on the future handouts, but how do you want to describe sort of this region over here, this amide region? Is there any terms we can use to describe it? In terms of solubility or light dissolves light? Polar. Any others? What about in terms of mixing with a solvent? You familiar with terms like hydrophilic? What does hydrophilic mean? Yeah. Which portion of that molecule is more hydrophilic? The amide portion or the benzene ring portion? The amide portion. Okay. What does hydrophobic mean? Which side is more hydrophobic, the benzene ring or the amide? Yeah. See, it's nothing but van der Waals, non-polar. I mean, van der Waals comes from, it's essentially non-polar. By bumping into something that gets that very fleeting weak polarity, but it's so weak. Not a lot of polarity over here. It's not going to like water. So the question is, as this gets bigger, it's going to start hating water, even though it might have that. Okay? For example, let me go ahead and show you this handout here. I don't think it's in your handout because it really needs to be colored to illustrate it. This compound up here, on the nitrogen we have R groups. Those are defined below. First compound R is methyls, that's 2 methyls, or 2 ethyls, or 2 propyls. And what we have here is, we're mixing the compound with cyclohexane and water. First off, do cyclohexane and water mix? No. I mean, cyclohexane is just that. Does that look like it's going to like water? No, and it does not. It forms 2 phases, like oil and water. Okay? Here's the 2 phases. Now we put the compound in there and maybe shake it up. Okay? Compound is yellow once dissolved. It's red in the solid form. That's why it's called these here. With just methyl, it mainly goes into the water layer. If we increase the hydrocarbon portion, what happens? It starts wanting to go up in the cyclohexane layer. Now if we increase it to 2 propyls, what happens? it starts going completely into the cyclohexane. So the more we get this hydrocarbon, which is just very bland, nonpolar, the more it's going to start liking cyclohexane salt. Question?
When we say something is hydrophobic, is it also lipophilic?
Yes, we could have said that. What does lipophilic mean? It likes lipids. What is lipids? Fatty. What is fatty? Fatty is typically hydrocarbon. Your lipids like cholesterol, triglycerides, if you look at those structures, they get a lot of hydrocarbon in them. I mean, cholesterol has an OH, cholesterol. The rest of it is all hydrocarbon, pretty much. We'll see those terms somewhere along the way, or just in homework problems or something. Okay, so that's terminology. We can discuss our molecules. Any questions about this? Now again, you would never have been able to predict which layer this prefers. This is a relative. And as we get more hydrocarbon, the more it likes cyclohexane. That makes sense. Okay, various solvents, some below. Water is sometimes called the universal solvent. Basically, it's good solvent for salts, ionics. Your organic compound has to be pretty polar to dissolve in water. Sugar dissolves in water, but not easily, right? You have to heat it. Look at the structure of sugar. It's got a lot of OH groups on it. Those OH groups help it dissolve in that water. Typically, organic compounds are going to prefer organic solvents. That's the most general like. Organic likes organic. All right, but that can vary tremendously. Here's some solvents. You need to start getting familiar with them. You do not have to memorize these solvents here. This is sort of a reference list. Okay, you'll see these in lab. You do need to just develop your knowledge of solvents as we go along. I've divided these into polar and nonpolar. Okay? Polar, nonpolar. My division and many chemists' division like this is your polar solvents. These are over here because they're soluble in water. They mix with water completely. If you mix water and DMSO, it'll be one phase completely. Water and acetone, one phase. These over here, which I call nonpolar, do not mix with water. They form two phases. Now, this is what we mentioned last time. All these over here, diethyl ether is a polar molecule. Okay? It's got a molecular dipole moment. If you draw it, they don't cancel. So why am I calling it nonpolar? Because I told you my classification is your nonpolar solvents, I'm calling they're not water soluble. Okay? See, it's hard to say. Why is this not water soluble, but that is? They both look similar number of carbons. Actually, this has one more carbon. They can both hydrogen bond to water, but this one's soluble in water and that one's not. There's a fine line there. Okay? Dichloromethane, toluene. That's pretty nonpolar. This is the only truly nonpolar solvent up here. Importantly, the solvents that don't mix with water are useful for extractions, liquid-liquid extractions, where one liquid pulls molecules out of the other liquid. For that to happen, these two solvents have to separate. You can't do an extraction with these. Okay. Over here you can read that. Developing your sense of solubility. You have to just sort of do as we go along, things we do in lab. This is shown here. It's also shown in the next handout. I'll briefly mention here, not much. This is an extraction process. Separating these two compounds You got a mixture of these two. One way to separate them is an acid-base extraction. You dissolve these in dichloromethane. Put them into your separatory funnel, which is in your drawer. Dissolve. Add sodium hydroxide, which is aqueous. It's not going to mix with the dichloromethane. It will only mix if you shake it vigorously, like your oil and water or your oil and vinegar and for your salad. Shake it up. But it'll separate once it's no longer shaken. We can separate these compounds because this compound is not acidic. It will always remain in the organic solvent. This compound, though, what's the name of that functional group? Carboxylic acid. Okay, this is sort of condensed. All right. Carboxylic acid could be CO2H, it could be COOH, or you could draw it out with the carbonyl and the OH. Okay, it's just condensed. This type of thing you just have to see as we go along. All right. Carboxylic acid will react with the base to form what? A salt. Once you get the salt form, it's going to prefer water. Ionics prefer water. There can be some exceptions to that, but for us, ionics prefer water. Even with the big hydrophobic benzene ring, still ionic. Prefers what? Water. We'll do this, we'll go back through this process again after we cover, guess what, acid-base chemistry. It's the next handout. But it's a very similar thing in your solubility lab. If you can get something to become ionic, it'll be soluble in water, most more likely. Where a neutral organic is not typically going to be soluble in water. Unless it's highly polar, like sugar or something. The type of thing you need to be getting a handle on. Okay? We'll go back over that after we do acid-base. A couple miscellaneous things here. Why are IMFs, what are they good for? Here's an example of Crestor. What is Crestor? HMG-CoA reductase inhibitor. Biosynthesis of cholesterol, inhibiting that process. This is a schematic of Crestor bound to the enzyme, the HMG-CoA reductase enzyme. How does it bind to that enzyme? That's one way. Various IMFs. There's one right there. There's an H on an N, hydrogen binding to what? Lone pair of a fluorine. There's your acceptor, there's your donor. There's a lone pair of an oxygen, hydrogen bonding to the H that's on an N. Sometimes you got to be like, what the heck is going on there? That don't look right to me. Looks like they're trying to say an oxygen, hydrogen bonding with an oxygen. Yeah? Does that look reasonable? They should have showed this associated with the H, right? See that? Somebody fell asleep or didn't really know what they were doing on drawing this. But see, you guys are going to be able to recognize things aren't quite right. Yeah? What is this? Hydrophobic bonds. What is that supposed to be? That's another name for van der Waals or London or something. All right? Is it really a bond? No, it's an IMF. Like hydrogen bond is not really a bond. What is this? That's just hydrocarbon portion coming off of this ring. What is it associating with? Amino acids that just have hydrocarbon side chains. They're calling it hydrophobic bonds. That's pretty weak association, but maybe it's just enough to make this molecule bind to the enzyme even stronger. I think there's some ionic up there. But there you go. IMFs are very important. what we got down here? Soap. Most of your soap is like this. You have a sort of an ionic end called the polar head group. And then you got this long fatty chain. Look on your shampoo bottle next time you take a shower. Some of the first ingredients probably going to be sodium myristate or something. It's a sodium salt of some type of long fatty acid. What's a fatty acid? That's this long fatty portion or fatty or lipid portion. And then the polar. Why does this act as a soap?
Because part of it likes water, the other part doesn't.
Part of it likes water, which is what you're bathing with, unless you're bathing with acetone. Right? Right. But how does the water rinse off the oils that are on your skin that you ultimately those are oils. Water didn't like oils. Well, this part associates with the water, that part associates with the oil, and it sort of brings it all together. It helps bring the molecules together, like an arbitrator. There's also things like this known. That is the grease molecule. The fatty ends can associate around it with the polar portion sticking out, and the polar portions associate with the water. The polar portions are going to be able to hydrogen bond with the water, with those oxygens. Y'all seen something like that before? Yeah? Yeah, I mean, micelles, that type of stuff. Cellular stuff. I mean, cell membranes. Yeah. Real quick, let's finish up here. We need to move on. Here is two drugs, Prilosec and Nexium. For, what do they use for? Upset stomach type stuff? Gas? Acid reflux? Yeah. What's the difference in the two? Prilosec versus Nexium?
The charge on the nitrogen.
The only difference is the H has been removed, and now you have an anion on the nitrogen. And since we got a minus, you got to have a plus. Plus is magnesium. Now, since that's 2 plus, you got to have 2 of these. So that's why that's in brackets. 2 of the molecules to go with 1 magnesium. It's just a magnesium salt. That's the only difference. By the way, once we do acid-base, what's going to happen to this when it gets to the stomach, where there's lots of HCl?
It's going to bond, yeah, hydrogen.
Yeah, with HCl, it puts the H back on. So don't spend all your money on Nexium, just take Prilosec. Because once it gets to the stomach, it's the same thing. The drug company just got a new patent because they probably said that this dissolves faster in the stomach and thus the onset of action is quicker. Why would it dissolve faster in the stomach? Because it's ionic, and the stomach is aqueous. But as soon as it dissolves and comes into contact with the aqueous acid, it's going to protonate. So it's really the same molecule. But Nexium is still on patent, I believe. Okay. We did the back. There's a miscellaneous sheet on the back. The back it says inductive effects. Inductive effect is basically a result of your dipole. Dipole through a single bond. And really that's all we looked at so far when we did like HCl, the dipole. That's an inductive effect. It's just a name for that. You can look at that and see if you can rationalize those questions there. Why ampicillin is more stable than just regular penicillin. It used to be penicillin you have to keep in the refrigerator because it's more unstable. Is that still true? Pretty much penicillin these days is not used much anymore. Okay, acid-base chemistry. As we move into this, any questions? Acid-base. Okay, acid-base, hugely important. Are there any questions that you will hopefully be able to answer by test time? Here also, Ultram. Let's look at this here, back to the first page. Okay, Ultram. Show the complete Lewis structure of the HCl salt that is formed upon treating the free base with HCl. This is called the free base. It's the basic form. It hasn't been propagated yet. React with HCl, what do we get? To be able to show full Lewis structure and understand reactivity. Where's the basic site in that molecule? Yeah, it's going to be the nitrogen. Okay? So we'll get to things like that. First thing is your acid-base mechanism. You have got to know this mechanism. You've got to know how an acid-base reaction takes place. Unfortunately, you guys don't know that. You've been through Gen Chem 1 and you've been through Gen Chem 2, which is largely acid-base, right? Wasn't Gen Chem 2 acid-base? Yeah. I don't understand why you don't know an acid-base mechanism. The basic molecule is going to have a basic atom. And the basic atom is going to have a lone pair. We're talking about a Bronsted-Lowry acid-base. What's the definition of Bronsted-Lowry acid?
Donate some.
Proton donor protons.
We donate a proton.
All right, let's maybe ask that a little bit later. Okay, in this scenario, we've got a basic atom. In this scenario, this is sort of your big molecule, okay? Big molecule is a base. But it's going to have some type of atom that's basic, an atom. What part of the atom? The lone pair. The lone pair, now I think some of you wanted to say it accepts the proton. It don't accept it, it takes it. Okay? Get rid of accepting and say it takes it. That's a more active term. Doing something. Okay? This is H bonded to some Z. That's sort of generic for some electronegative atom. This could be maybe HCl, where Z is chlorine. Okay? These electrons, whenever we do mechanisms, we will start by saying these electrons. Everything will be these electrons. The electrons are doing something. You've got to identify which electrons you're talking about. I circle them usually and say these electrons. I'd recommend you do the same thing. These electrons make bond to H. That's what the arrow means. WDAM. What does arrow mean? When this makes a bond to H, well, H only makes one bond, so it has to say see you later to the Z. But hold on. That's a dipole there, right? Z is very electronegative. Otherwise, it wouldn't be an acid. That chlorine is already pulling those electrons, right? It's already a dipole there. Do you think chlorine would like to have these two electrons and just take them? Yes, it would. These electrons bond to the H, and these electrons get pushed onto the chlorine, and this is bond breaking. Electrons move on to chlorine. Chlorine has 3 lone pairs here. If this moves on to chlorine, how many will it have then? It will then have 4. These 2 electrons move on to chlorine as the 4th lone pair. Now, I'm just drawing the new one there. If it's chlorine, there's 3 on it already. I'm just drawing the new one. So if you want to stick with the chlorine, it would be Cl, and there's 3 there that were there to begin with. But now the basic atom is bonded to the H. And this used to be what on the basic atom? That used to be a lone pair. But now the lone pair is bonded to the H. Okay? Every acid-base reaction we do in this class in Organic 2, and really from here to eternity, is right there. And every one you do, you should do that. Right there. Don't get 2 weeks down the road and forget about this. All right? Because if you do, then you're going to have trouble. You're not going to know what you're doing. Here it is. What do you have to do? You got to identify which is the basic atom. You got to identify your acid. But if you're dealing with HCl, that's easy, right? So you have to learn acids, but it's the same mechanism. What's that?
Z would be negatively charged because that's an extra.
Good point. And I didn't show any charges up there at all. That's very generic. If it's Cl, it would be minus, yeah. Yeah. But it didn't have to be minus. So that's why I didn't show it. What it has to have is an extra lone pair, because that will move on as an extra lone pair. But it may not always be minus. You do have to know what the ultimate charge is. That's why we learned how to determine charge. And you always have to show appropriate charge. Question?
Would it work the same way with like an acid that had a polyatomic ion attached to it?
Like what acid?
I don't know. Yeah, sure. Sulfuric acid.
Yeah, I mean sulfuric acid just applies 2 H's. You can do it twice.
Okay.
Any bronzostyrolic acid base reaction, there it is. Phosphoric acid, you'll be able to do it 3 times. Phosphoric acid tripro. Okay, I think everything is what I just explained there. Charges of any, you need to be able to show them. Basically, that's it. We'll do examples. Basically now you should be able to show the product of that right there. We know what the acid is, HCl. You just got to identify what's the basic atom, right? But we'll talk about that along the way. Somebody's already said the answer. Okay? Okay, so here's acid base, and all that stuff up there you did in Gen Chem 2. You spent a whole semester on it. Let's start right here. Basically, I used to start right here and show you the mechanism, but then I said, well, I'm going to make a fresh page. It's basically a repeat. This is showing you where water is the base, and I just showed you HA. Sometimes the other portion of the acid is called A, sometimes it's called Z. What's the acid-base mechanism? The lone pair does what? Bonds to the H. What happens to the electrons that are there? They move on to the whatever bonded there. And so the A now has a lone pair. In this scenario, I showed charges because I'm dealing with water. Water becomes H3O+. I didn't show a full Lewis structure. But now the oxygen's bonded to another H. That's what this arrow means. And we got A-. So it's no different from what I showed. Oh, there's the full Lewis structure. Now one of the lone pairs of water is bonded to an H. Right? That's exactly what was on the previous page. Okay, pKa, we usually use pKa's, you know all that. We need to get familiar with pKa's, various acids. HCl is a strong acid, pKa like -7, -8, -10, something very, very low pKa. Acetic acid. Well, forget about the methyl. What is that? Carboxylic acid. pKa of about 4 to 5 or so. With acetic acid being an example. Acetic acid is considered a weak acid. Put it in water, it only partially ionizes. What type of functional group is this? Alcohol, pK about 16. So it's not nearly as acidic as a carboxylic acid. And then this is just a hydrocarbon. Okay? That's a pK of greater than 40. That's not acidic at all. There's an extensive list of, or a more complete list of pKa's in the back of your workbook lab manual. Basically, we'll see more of those. Hopefully by the end of Organic 2, you'll know most of those on the back of the workbook. Okay? Those right there I would know now. We'll perhaps see others. Why the trend there? Maybe you could give a rationale now. But why is acetic acid more acidic than the alcohol? Well, let's systematically look at why. There's four main things that affect this. Affect acidity. What makes one compound more acidic than another? Later on, we'll talk about basicity. And now acidity. Four things are here. We'll look at them each. First one is electronegativity and size of A. A is the thing that the H is bonded to. It can either be one atom, like HCl, or it could be an atom that's connected to lots of other stuff, a huge molecule. Okay, first is electronegativity of these two. Let's consider H2O and HF. Which is more acidic? Some of these you should already know.
HF.
Okay, HF. Why? Because fluorine is more electronegative than oxygen. Okay? Importantly, you need to consider the stability of the conjugate base. What is the conjugate base of HF? F minus. What's the conjugate base of water? Hydroxide. This is what you need to consider the stability of. That's what I said here. Which is more stable? F minus. Why is it more stable? Because it's more electronegative. What does that mean? It likes electronegative better. Fluorine is more stable. It likes, yes?
So hydrofluoric acid isn't a strong acid, right?
HF is, I don't think, considered
It's
a
not a strong acid, but fluorine is more electronegative than chlorine. Is that just an, like we're going to have to realize that's an exception?
No, we'll cover that's a size factor. We'll cover size after electronegativity. Okay, which is more stable? F minus, because it likes being minus more. That's what electronegativity means. Everybody know how to predict electronegativity? Okay. So, since F is more stable, which one's more willing to become minus? That one, because it doesn't mind becoming minus. And since it's more willing to become minus and give up the H, we call that a stronger acid. Okay? What are we considering? The stability of the conjugate base. What's this answer based on? Electronegativity. Okay? H2O or NH3, which one's a stronger acid?
H2O.
What do we need to consider? We need to consider hydroxide versus what? Versus the conjugate base. Which one's more stable? O minus or N minus? O minus, more electronegative. This is more stable. That means that water is more willing to give up the H and form this. That guy's like, I don't want to become that. I don't want to become minus as much. So I'm not going to give up my H plus. Okay? Which is more acidic, water or methane? I mean, hydroxide versus, this would be CH3, the lone pair minus. Carbon is not that electronegative. Carbon really hates being minus. We'll see it being minus. Oxygen doesn't mind being minus. So it's much more willing to give up and become, it's much more willing to act as an acid. those are electronegativity. We also have size of the atom. We about out of time? Okay. Please look ahead. Size of the atom. We'll then move on to number 2, 3, and 4.
Christy, are you coming home and drink?
I would highly recommend you do the warm-ups and the acid base and have plenty of questions next time.
I don't think I will. I'm not feeling it.
I forgot to mention this. Next week we'll be doing a distillation. I usually do that at the beginning of lab. Instead I'm going to do a video of it and hopefully post it tomorrow. It'll be a lab demo. Okay? Instead of me doing it at the beginning of lab. I will leave from every section.
I'll meet you. Why does it break your
Oops, I'm in the camera.
Is there any way I could like fit into a lab next week to do this week's stuff? Or is there like a certain time of day that I have to wait there and just do this?
You really want to talk to him. Each lab has a structure.
Okay.
He needs to make whatever policy he has.
Yeah, because I just don't want to end up with zero.
I can talk with him if needed. He should tell you how to proceed. Maybe you're just getting zero.
I'm not sure there's some information.
Is there